Symmetry appeals to our visual sense, and that thereby plays a role in our sense of beauty. However, perfect symmetry is repetitive and predictable, and our mind also likes surprises. So we often consider imperfect symmetry. So what is a symmetry? A symmetry is a mathematical concept as well as an aesthetic one. It then allows us to classify different types of regular pattern and distinguish between them. Symmetry breaking is more dynamic and is more dynamic idea, describing change in pattern. Say for example, the most familiar symmetric form is one inside which you spend your life. The human body is bilaterally symmetric, meaning that its left half is near enough and the same as its right. Another, which is called reflection, it is a mathematical concept, rule for moving things around. There are many different kinds of symmetry. The most important one are reflection, rotation, and translation, and less formally, flips, turn, and slides. So, a reflection is a symmetry in which one half is figured in a mirror image of the other across a line, like the left and right sides of the human body. Rotation is a symmetry where a figure is turned around a center or axis and still looks the same, like a flower with evenly spaced petals. Translation is a symmetry when a figure slides in a certain direction without turning and the pattern remains unchanged, like repeating tiles or a honeycomb.
This chapter talks about something surprising in nature, how patterns can appear on their own. At first, the author explains something simple. If you throw a pebble into a pond, you see circular ripples. The pebble caused the pattern. But what if the pond suddenly formed ripples with no pebble? We would look for a cause, because we believe patterns always have a reason. Then the chapter introduces a real scientific discovery. A scientist mixed some chemicals together, and after a few minutes, colored circles began to appear. Red and blue rings formed again and again, like targets. No one steered it, no one touched it. The pattern formed itself. At first, other scientists didn't believe this discovery because it seemed impossible. How can order come from something random? The chapter also connects this idea to something very important, our heart. Our heart beats because electrical waves move through heart cells in organized patterns. These waves move in smooth circles, the heart beats normally. But when the wave turns into spirals, the heartbeat becomes irregular. This can be dangerous. So the same kind of pattern that appears in a chemical dish also happens inside our bodies. In short, this chapter teaches us that mathematics is not just numbers on paper. It explains real patterns in nature, from ripples in water to chemical reactions to the rhythm of our own heart. Have you ever wondered why the universe isn't just plain and boring? Why do we see patterns, spirals in galaxies, hexagons and honeycombs, spheres and stars, instead of complete uniformity? In this chapter, we learn three ideas lies in the two powerful ideas, symmetry and symmetry breaking. Symmetry means balance and uniformity. It means that parts of something are interchangeable without changing its overall appearance. For example, a square looks the same even if you rotate it. A molecule like methane has perfectly balanced shape. Even viruses often form precise geometric structures like helices. Nature seems to prefer symmetry. At the smallest level, molecules are symmetrical. Inside living cells, structures like microtubules show organized, repeating patterns. On a larger scale, stars and raindrops are spherical. Galaxies form spirals. Honeycombs form hexagons. The same patterns appear again and again, across completely different scales of existence. But here's something interesting. Perfect symmetry doesn't look like a pattern. It looks like sameness. If every part of a system is identical, we don't recognize it as special. We just see uniformity. In fact, the laws of physics are the same everywhere in the universe. Every electron is exactly like every other electron. Every region of empty space is equivalent. This idea is called invariance, and it was central to Einstein's thinking. No place in space or time is special. So here's the big question. Is everything symmetrical and the laws of physics never change? Why is it that the universe is completely uniform and unchanging? Why do we have structure, life, and complexity? The answer is symmetry breaking. Symmetry breaking happens when a tiny disturbance disrupts a perfectly balanced system. The chapter gives an example of a chemical solution that is completely uniform. But if something very small disturbs it, even something almost invisible, the balance is broken. A small spot forms, and from that moment, patterns begins to spread. An almost insignificant cause can produce a large-scale effect. That is the power of symmetry breaking. Symmetry creates stability, but symmetry breaking creates diversity. Without symmetry, nothing would hold together. Without symmetry breaking, nothing interesting would exist. This idea explains why nature is both orderly and complex at the same time. What I find most powerful about this chapter is a reminder that even something tiny can change everything. A small imbalance can shape galaxies, cells, and life itself. In conclusion, symmetry explains why nature is balanced and consistent. Symmetry breaking explains why nature is a dynamic and full of patterns. Together, they explain why the universe is just not uniform, but beautifully structured. And maybe that's what makes it so fascinating.
A symmetric model can have many possible states, but in reality, only one state becomes actual. Small disturbances or imperfections push the system to choose one outcome from all the possible symmetric options. This is why symmetry breaking is important in understanding pattern formation. The mathematics behind it shows that even if a system starts perfectly balanced, tiny changes can lead to organized and visible patterns. Because of this, symmetry breaking has become a key principle in explaining how structure forms in nature. For example, sand dunes in the desert can be explained through symmetry breaking. If a wind blows steadily across a flat sandy surface, the system is originally uniform and symmetric, but when the symmetry breaks, patterns begin to form. Parallel stripes at right angles to the wood become transverse dunes, and if more symmetry breaks, wavy ridges called Bartonoid dunes appear. The same mathematical idea applies not only to desert, but also to rivers depositing mud or shallow seas shaping the seabed. Over time, these patterns can even become preserved in rock, showing that the same symmetry breaking principle work across many natural systems.